Hello, boys and girls. Our study guide today starts with just simple mole conversions. Now, remember that some of these problems are going to look very similar to one another, even though they're not the same type. So we have mole conversions where we're just simply converting units to one or another, like moles to grams, particles to moles, and things like that. And then we have the stoichiometry problems, which ask us to do, it kind of looks like you're doing the same thing. But it's very important to look for certain things so you know exactly what you're supposed to be doing. So when it comes to mole conversions, that means only using those three conversion factors: moles to grams, moles to particles, and moles to liters. You will not be provided a reaction. A reaction is not necessary. So when it looks like I'm asking you, I'm giving you numbers and you're building a board to get the answer, if a balanced chemical equation is not provided, then it is just a simple mole conversion where you're going to build your board and put in the correct conversion factor you need to make that change. All right? So the very first one on your study guide says, what is the mass of 9.91, excuse me, let me write that over a little bit, 9.91 moles of magnesium chloride. And I even give you the formula, MgCl2. All right? And again, I want to know the mass of that. I am asking for the mass of that. So we're going to chunka, drop. And remember, regardless of what problem we're doing, we always drop what comes after the number. So we're going to drop moles of MgCl2. All right? Now, this is where we go and we say, well, which one of those conversion factors will change these moles into mass? Well, that is the conversion factor that says 1 mole equals the molar mass in grams. All right? So how do I fill in this empty space? I add up the masses on the periodic table. So when I go to my periodic table, and I add up the mass of 1 magnesium and 2 chlorines, because that's what the formula has. Each magnesium is 24.31, and each chlorine is 35.45. So you have 2 of those chlorines. So when you add that up, you should get 95.21. So this is my conversion factor. And what I'm going to do is I'm going to karate chop it right down the middle, right? Hi-ya, right there. And I'm going to put it in. Well, as you can see, the mole half has already been determined that it has to go in the bottom. So I put the 1 mole in the bottom, and then in the numerator goes the 95.21 grams. The moles cancel out. I'm going to be left with grams. So this is when I pick up my calculator, when I get to the unit I want. And I'm going to do 9.91 times 95.21. And I get 943.5. So if I was being particular about your digits, then I wanted 3, then that 5 would cause that to round up to a 4, and then you would lose that. And it would be 944. Okay? All right. So that's the first one. The second one is another conversion. This time, it says to find the moles of carbon dioxide gas at STP in 326 liters. All right? So we've got 326 liters. That is our known. and we want to convert that to moles. So I say to myself, after I chunk a drop, so this was the given amount, 326 liters. I chunk a drop and put liters on the bottom. The conversion factor that I use, if you remember, you can find everything except the molar mass one, you can find right on the front cover of this. But it is 1 mole equals 22.4 liters. So that's what I'm going to plug in right here. So where the liters are, that's where I'm going to put the 22.4, and the 1 mole goes in the top. So keep in mind that if this would have started with 326 moles, then this would have been flip-flopped. So remember, it's not that something always goes on the top or something always goes on the bottom. It's totally decided by the unit you start with. Whatever unit you start with is the part of the conversion factor that goes in the denominator. Okay? So to find this answer, I'm going to enter 326 divided by 22.4. And I get 14, and it says 0.55, so I'm going to round that to 14.6 moles. 14.6 moles. All right, let's move on to our other one. Our last conversion we're going to practice asks us to find the atoms of Ti, which is titanium, on your periodic table. Find the atoms of titanium in 12 moles. Okay, so we're told we have 12.0 moles of titanium. All right, we're going to chunka. Remember, whatever is here goes here. Now, I think to myself, what do they want me to change these to? They said atoms. So remember, atoms is a particle. So this is where we're going to use Avogadro's number, right? 1 mole is equal to 6.022 times 10 to the 23rd atoms. And by the way, I see where a lot of y'all make mistakes with this number. If you are in doubt, look it up. It is on the very front cover of your reference tables. It's in your notes. So don't guess the wrong number for Avogadro's number. You got it available to you. All right, so this is where I'm going to karate chop this in the middle, split it up. The 1 mole goes in the denominator this time, and Avogadro's number goes in the numerator. The moles cancel out. So we are going to say 12.0 times 6.022, second 23, and I get 7.23 if I round that last digit up, because there's a 6 next door to it, times 10 to the 24th. Okay? All right. Now, let's move on to the second section in our study guide. In the second section, we're doing percent composition, okay? So percent composition is the formula where you take the mass of the part, so whatever element I'm wanting the percent composition for is your part, over the mass of the entire compound. So for our practice today, the compound we're given is Al2O3. And I am just for extra practice, I'm saying let's find the mass percent, or the percent by mass, or the percent composition. Remember, it has multiple names of each one of these elements. So let's start with aluminum. Let's say the problem said, find the percent composition of aluminum in this compound. All right, our part would be aluminum. There are 2 aluminums. So I would go to the periodic table, I would look up aluminum and get the mass and times it by 2, because there are 2 aluminums in that compound. So the aluminum ends up being, each aluminum is 26.98, and we've got 2 of those, so that's 26.98 times 2 for that aluminum. And then the oxygen is 16 times 3, okay? So the aluminum, if I'm doing the percent of aluminum, then the part will be 53.96, all right, divided by the mass of the entire compound. So I'd have to sum all of that up, and I get 101.96. I times it by 100 because I want a percent. So the mass percent of aluminum would be 53.96 divided by 101.96 equals times 100 equals 52.9%. So that equals 52.9%. All right? Okay. Now, let's say this time I were to say, what is the mass percent of oxygen in aluminum oxide? So then we'd be doing the percent of oxygen. Remember, that is not a deadly, it is in a compound, okay? So I can just put that O there. This time my part is oxygen. There's 3 oxygens and there's 16 each. So that is 48 is my total mass for oxygen. And then I'm going to do my total, got lost there a minute. So it's going to be pretty close because as you can see, 53 out of this and 48 out of this are going to be pretty close to the same thing. And we know that if that's 52.9%, then I can expect oxygen to make up the rest of it, right? So 48 divided by 101.96 equals, and then that gives me 47.1%. And that makes total sense because together they equal 100%. All right, okay. So you can expect to see maybe 3 or 4 of these on your tests where either like this, I will ask you to do each element in the compound like I did here, or to just be a question where I specifically pick one out. All right, now let's move on to the part that is the stoichiometry. All right, so the very first problem I have, I'm going to go ahead and write my reaction up here. CH4 plus 2O2 yields CO2 plus 2H2O. All right. So that is actually not the first one. So let me back up a minute. Sorry, my bad. I skipped one. The one we're doing right now is a GNO3. And then 2 of those plus H2S yields Ag2S plus 2HNO3. Okay, so this is our reaction. Here's my arrow. And the problem basically says to determine the moles of the hydrogen sulfide, or you can call it hydrosulfuric acid. It kind of has some multiple names here, but the H2S, to define the moles of that. So I'm going to put a question mark there so we know that we are solving for the moles of that, and that will react with 9.88 moles of the AgNO3. So I've got 9.88 moles of the AgNO3. So as far as I'm doing it this way instead of writing the whole problem down for you. You've got it on your study guide, so there's no reason for me to write it all down. So again, we are solving for the moles of the H2S. That makes this my unknown, right? and we are told that we have 9.88 moles of this. So this makes this my known. All right? So step 1 continues when we get our board started. So I take whatever value they gave me, which was 9.88 moles of the AgNO3, and I chunka, drop. Again, I'm going to bring moles of the AgNO3 here. Okay, all of that is step 1. Again, let me repeat. Step 1, let me get my little steps right here. You know, I love my little papers. Step 1 is for you to identify the known and unknown. All right? This is what we're solving for. That's the unknown. This is the amount given, so this is our known. We put our known, our given known in the board, and we chunka drop. Now we are at step 2, convert to moles. Well, look at there. I have moles. I don't need to do step 2, right? So if you're on your flow chart, you would not need to choose one of those 3 because you're already in moles. So where do we go to next? The mole ratio. And if you remember, the mole ratio is unknown over known, okay? So that's what's going here. It's step 3. I'm just going to put a little 3 right here, mole ratio, just so you can see that. Okay, so it's unknown, which is this, and there's a understood 1 coefficient, so 1 mole H2S over the known, which is 2 moles of that. Cancel out. Okay. Well, there's a possibility of a step 4. If we need to convert the units of the H2S to something else. And when I look back at my problem, it said, how many moles? So I do not need to do step 4 to convert that to anything else. I want moles, and as long as you want moles, if the problem says how many moles, calculate the moles in a stoichiometry problem, then you're going to stop right here and not do step 4, okay? So let's go ahead and do this. 9.88, and then we're going to multiply straight across, which is just times 1, divide it by 2, 4.94. And that is moles of H2S. That's our answer. Okay? All right. So remember, I want to make this clear because you're going to end up with a lot of problems that look the same on one test. If it comes with a balanced reaction, it is a stoichiometry problem. It may ask you for the limiting reagent, or it could be a limiting reagent. So limiting reactant and stoichiometry are going to have the reaction with them. If it does not have the reaction, do not follow those steps on the flow chart. It is not that type of problem. It is just a simple conversion. All right? Okay. Let's move on to our next stoichiometry practice problem. And this time, I'll put it up for real this time. CH4 plus 2O2 yields CO2 plus 2H2O. Okay? And again, instead of writing the whole problem as I read it, I'm going to mark the stuff I'm given. So this one says, to calculate the molecules of water. So what I'm looking to find is the molecules. So I'm just making myself a note of water. That's what I want. Okay? And because I'm looking that means that is my unknown. Okay? If I'm solving for it, is my unknown. Okay? Produced by the combustion of 7.20 grams of methane. And methane is that, all right? And it tells us we have 7.20 grams of the methane. And because I know how much I have of that, then that is my known. Okay? All right. So now that I've identified my known and unknown, I'm going to continue with step 1 and start my board with that value that I know. 7.20 grams CH4. Okay? I'm going to chunka drop grams CH4. All right? Is everybody with me? This is step 1. Known, unknown. Start your board with what you're given about the known. Chunka drop. Okay? Now what we're going to do is step 2 says, if you're on your flow chart, you're at step 2, it says convert to moles. Well, as you can see, I don't have moles. I have grams, all right? So this is where you're going to look under step 2, and you're going to pick the one that will change the grams into moles. And that is the one that's the molar mass one, right? So when you look on your flow chart and you find it's the second one on your flow chart under step 2, you're going to see that it says on the bottom to put the molar mass of that. So you've got to go to your periodic table. You've got to add up carbon and 4 oxygens. You should get 16.0, I think it's 42. I hope I can read my writing. Okay, 16.042. Let me spread that out a little bit. 16.042 grams of CH4. All right, and then in the top, it tells us to put 1 mole of the CH4. Remember, CH4 is my known. So it says 1 mole of the known over molar mass of the known, okay? And CH4 is your known. So that gets us through step 2. So we move on to the next step, which is step 3. Remember, step 3 is never optional. So that is something you know you have to do, okay? So this was step 2. This is step 3, which is the mole ratio. So if you remember with the mole ratio, it is unknown over known, right? So my unknown goes in the numerator, 2 moles of water, and my known, 1 mole of CH4. And remember, it says coefficient mole unknown, coefficient mole known, okay? So I need to make sure that everything cancels out except for the water. I have moles of water right now. But when I look back up to the problem, even though I want to know about water, I specifically want to know about molecules of water. So that means I have to do a conversion here. I have to do step 4 and to convert these moles of water into molecules of water. So again, under step 4, I'm going to pick the correct conversion that will make these molecules. And if you look under step 4, I'm pretty sure it's the very first one, because molecules is a particle. And what it tells us to do, and I hope I'm not running out of room here, is to put the 1 mole of the unknown, which is the water, and then on the top, use Avogadro's number of, again, the unknown, which is the water, okay? Everything should cancel out except the molecules of the water. Remember, I use MC for molecules, just cause. So, what we're going to do is we're going to multiply straight across the top. There's only 1 number in the denominator, so we can just divide without parentheses. So we're going to do 7.20 times 2 times 6.022 second EE23 equals all divided by 16.042. And I get 5.41 if I round that last digit right there up 1, because the next door's a 5. Or times 10 to the 23rd. All right? Okay. Good deal. Now, we got 1 more practice problem to do, and it is going to be a limiting reactant. Okay, here's the good news. You remember in the class how we were doing all the multi-step, like you first had to identify the limiting. Then you had to do the stoichiometry with the limiting to get the theoretical yield, and then do the percent yield. On the test, I'm not combining things like that. I'm doing separate questions for everything. So it's not one question doesn't build on another. So the limiting reactant problem you'll have is just simply identifying the limiting, period. Okay? You're not going to then have to take it and do something with it. I'll have stoichiometry problems separate than I have a limiting problem. So let's practice a limiting problem. And again, it's going to come with a reaction as well. All right, so remember, a limiting reactant is just that. It is a reactant, which means it's got to be one of these, right? So always know that. So if I have 4 answer choices and I list every single one of these, please know that it can only be those 2 things. All right? So the question says basically, what will be the limiting reactant if 9.76 grams of the ammonia react with 10.11 grams of the oxygen, okay? So these are the amounts I have, 9.76 grams of this reactant and 10.11 grams of this reactant. And I have to figure out which one's going to run out first. So if we remember our rules with limiting reactant, the very first thing we have to do is to convert each amount to moles. So if I'm not fortunate enough to be told I have so many moles of this and so many moles of this, I have to convert them to moles. So I'm going to have to do that. So I'm going to take the 9.76 grams of the NH3. And again, how do I change grams into moles? I use molar mass. I'm going to chunk a drop so that I know that the molar mass has to go in the denominator and the 1 mole has to go in the top. And when we add up the mass of 1 nitrogen and 3 hydrogens, we get 17.034. Okay, 17.034. I apologize. That's all. I didn't leave myself room. 17.034 grams NH3. All right, so let's figure out how many moles of that I have. 9.76 divided by 17.034. And I get 0.573. I'm just going to round it. Just keep like 3 digits. Okay? All right. So that's 0.573. Okay? And that's moles of the NH3. Now let's figure out how many moles of oxygen we have. We're told we have 10.11 grams of oxygen. Please don't forget that that's a deadly. Therefore, when you get its molar mass, because remember, the way we convert grams into moles is we use its molar mass. So you have to remember to add up 2 oxygens, not 1, 2 oxygens. Oxygens are 16 each, so 2 of those is 32, okay? So we're going to say 10.11 divided by 32, and I get 0.316, and that is moles of oxygen. We can't stop here. This is not where we determine the lower number, okay? Remember, there's another step we need to do to know the limiting. We have to divide each of these mole amounts by its coefficient and compare the quotients. So let's do that. So the quotient of the ammonia is 4. So I'm going to divide that by 4. The quotient of the, I'm sorry, not the quotient, the coefficient, my bad. The coefficient was a 4, and oxygen, the coefficient is a 5. these values are the quotients, and the lower one of these will give us our answer. Okay, so 0.573 divided by 4, I get 0.143. And for this one, I get 0.316 divided by 5. And I get 0.063. So this is most definitely the lower of the two quotients. Therefore, the oxygen is my limiting in this particular question. Okay? So the oxygen would be, this would be my limiting reactant. The oxygen in this particular problem with these particular amounts. I might give you this exact same problem, but if the amounts are different, then it might not be oxygen. Okay? All right. So that pretty much gives you a sneak peek and some practice on all the other problems. The only other type of problem you're going to see is a percent yield. And again, because I didn't do a multi-step problem, any of the percent yields you get will just be standalone percent yields where I describe a situation where the math gave you one number and then you actually recovered or got a certain amount of the product in lab. And it's up to you to apply this formula that the percent yield is equal to the actual yield times actual yield over theoretical yield times 100. Okay, so just gonna try to look and see if I see any other little notes that I've got on anything, any little last minute things I've got. Hopefully you've been working these along with me and utilizing that play and pause button so that you can be as independent as possible and then just get that, that affirmation and that support that you need as you need it. It doesn't really work that well for me just to sit here and work problems with you in real time because you need to be kind of thinking through the steps first. So I think I've pretty much covered about everything I need to. Good luck.